In this problem, we have this mathematical representation of a wave, and the problem asks us to find the speed of the wave using the wave equation. Now, this is a very interesting problem because it's very, very easy to get the correct answer using the wrong method. Now, what do I mean by that? Well, if you know your wave formulas, then you know that the speed of the wave is very easy to find using this formula here, where we have that the speed of the wave is equal to the omega, the angular frequency, divided by k, the angular wave number. Now, plugging in the obvious values for the angular frequency and the angular wave number, we can find the wave speed this way. And it turns out, if we plug in our values here, we get an answer of 1.75 meters per second. And we get that using 7 inverse seconds for the angular frequency and 4 inverse meters for the angular wave number. And that will get us the correct answer. It is true that this is a valid way to find the speed of the wave, but it's important to note that this is not what the question is asking for. The question asks for you to find the speed of the wave, yes, but it wants us to do so by utilizing the wave equation. The wave equation is given by this right here, where we have the second partial derivative of y, the transverse displacement of the wave, with respect to x, the horizontal positioning of a particle in the wave, is equal to 1 over the wave speed squared times the second partial derivative of the transverse displacement of the wave with respect to the time. This is our wave equation. This is what we're asked to use to find the speed of the wave. So now that we've defined the wave equation properly, let's solve this problem in the proper way. Now, because we're looking for the speed of the wave, which is represented by v, let's isolate v. So let's multiply both sides of this equation by v squared. That way we'll be able to cancel it out of this right side here and get it onto into a numerator side of the left side, even though I mistakenly sort of wrote this close to the denominator. And then we'll have to divide both sides of this equation by the second partial derivative of y with respect to x. So that we'll be able to get v squared on its own. So let's do that here. And now we can see that this will cancel out on this side, the second partial derivative of y with respect to x. And then lastly, we'll want to square root this whole thing so that we can convert this v squared into a regular v. Now, doing all of that, except writing it out in a much more clean manner here, we can see that the speed of the wave, using the wave equation, is related by the square root of the partial second derivative of y with respect to time, divided by, and I wrote it as a slash here so it wouldn't be unnecessarily tall, I guess, the partial derivative of y with respect to x, the second partial derivative, rather. So we want to somehow use this equation to find the wave speed based on the information we're given here in the problem. So now that we have the formula we want to use, let's find the second partial derivatives for each of these terms so that we can evaluate this equation here. First, let's find the first partial derivative of y with respect to t. So let's solve this derivative here. So you want to take the derivative of this wave function we're given here, except we want to find the derivative of it with respect to t, where t is the variable of differentiation. So let's do this. So this is mainly a sine function, and if you're familiar with your common derivatives, then you know that the derivative of a sine function is equal to a cosine function. So let's write that out here while preserving the constant on the outside. Alright, and I've written this out as a cosine function now. And then we'll have to apply the chain rule. So let's multiply this entire thing by the derivative of the inside function, again with respect to t. So that means we're going to be treating this 4x as a constant because we're not differentiating with x as our variable there, just the t part here. So the derivative of a constant is just 0, so the inside becomes negative 7t, and the derivative of a constant multiplied by the variable of differentiation is just going to be that constant because of the power rule. So we're going to be multiplying this whole thing then by negative 7. So we now have a negative function here. Now, let's take the derivative once more so we can find the second partial derivative of y with respect to t. The derivative of a cosine function is going to be equal to a negative sine function. So I would rewrite this as a negative, except you'll notice that this negative sign that would appear there is actually going to be canceled out by the negative in the negative 7 here. So that's nice. So I'll write that out now. Alright, I have written that out now. And for the 7 I took it over to the front, and I decided to include the units that are associated with that as well, because I figured it would be worth including. And once again, we'll have to apply the chain rule. We're just applying the exact same chain rule we did before, since the function inside the sine or cosine function isn't changing. So let's just multiply again by the derivative of that, which is once again going to be negative 7. So in the end, we still end up with a negative function. Now, let's take the derivative, or the partial derivative, of y with respect to x. This is going to work mostly the same way. The only real difference that's going to come into play here is the way we apply the chain rule. Alright, so once again, I've taken the derivative in a similar fashion. I've turned the sine function into a cosine function. And now let's apply the chain rule once more. And since we're taking the derivative with respect to x, this time it's the t part here that is going to be seen as a constant and will turn into 0 when we take the derivative here. Instead, we're going to be deriving or differentiating this 4x here. So using a similar method with the power rule, this just becomes 4. So now we're just multiplying by 4.00 inverse meters. And now we'll have to take the second partial derivative using, once again, the same sort of process here. Alright, so once again I have done that. The derivative of a cosine function is equal to a negative sine function. So I've included the negative on the outside. And then once more applying the chain rule, we end up multiplying by this little 4 here. I'm not going to bother writing out the units again, you get the idea. But now what we want to do next is find out what we are going to get if we divide the second partial derivative of y with respect to t by the second partial derivative of y with respect to x. We want to know what this will look like, and it might help to do this before plugging it into the square root, just to simplify our calculations just a bit. Alright, so here I've written out the second partial derivative of y with respect to t divided by the second partial derivative of y with respect to x, right here in a much more clear manner. And these are the second partial derivatives we found in the previous steps up above. And I also carried all the negative signs to the left, so that it would be especially easy to see whether or not the terms were negative overall. And we can see that since both the top and the bottom of this function are negative, we can just cancel out those negative signs and make it positive. That will help us a lot, especially since we're supposed to be taking the square root of this. However, that's not the only thing we can simplify. In fact, when I write everything out in this much more easy-to-read manner, we can see that there's quite a bit we can cancel out here. These 3 millimeters cancel out. The entire sine functions will cancel out, since they both become identical after differentiating twice. So these can cancel out as well. And in fact, all we are left with, then, is this 7 times 7 at the top and this 4 times 4 at the bottom. So we can write that out as 7.00 inverse seconds squared divided by 4.00 inverse meters squared at the bottom. And all this is going to be equal to v squared. We actually want to take the square root of both these sides so that we can have just v on its own isolated. The square root of this is going to be equal to, effectively, it's going to be the same as taking the square root of both the numerator and the square root of the denominator. This is a 2, I should make that a bit more clear. So this is just going to be equal to 7 inverse seconds divided by 4 inverse meters. And that's what this is going to be equal to. And by now, it should become pretty clear that this is exactly the result we would get if we were using the oversimplified method I was describing above. See at the top where if we had just used the basic formula for wave speed, where we divide the angular frequency by the angular wave number, we would have done the same thing here. We would have divided 7 by 4. And of course, it's going to get us the same answer as well, an answer of 1.75 meters per second. And so, of course, that is our final answer. But I hope this illustrates now how you can get the same answer for a problem using different methods. Now, granted, in this particular case, it probably would have been much easier to just use this method from the start, but the problem asked us to show how it's done using the wave equation. So that is why we took the time to find the solution in this lengthier manner. But I hope this helps you understand the wave equation a little bit better now.